So this is our third in series of sets of problems of Newton's laws that involve objects that are interacting, and these are two unrelated and disparate problems. Alright, we have a 3 kilogram box sitting on a 7 kilogram box, and the 7 kilogram box is being pulled. Between the top box and the lower box, the coefficient of static friction is 0.55, and the coefficient of kinetic friction is 0.25. Find the maximum value of Fp such that the top box does not slide along the bottom box. Answer, of course, in newtons. All right, well, let's draw some free body diagrams. This will be top box, and this will be the bottom box. On the top box, there is a weight, which I'll call Fg, I guess, top T. But of course, it doesn't go through the bottom box, so there must be a resisting normal force, which I'll call F normal. And I'm just going to call it normal 1. There'll be multiple normals in this problem. All right, and that seems to be it. Let's go over to the bottom box. The bottom box has FGB for bottom. And of course, the floor is pushing on that, so I'll call it FN2. But then we have to be careful because this normal was coming from bottom on top box. So top on bottom box must also be exerting a force, which is Fn1. The same force, but pointing the other way. In addition, the bottom box is being pulled with some Fp that we're going to find. The problem here is actually not explicit and probably should be changed to be. So we're going to assume that this floor is frictionless. Only because we're not given anything. Right? We don't really know. So we can't. We'll make the simple assumption that allows us to proceed, which is that the friction is 0 there. So there's no frictional force from the floor. On the other hand, the box is not allowed to slide against the top box, so there must be some resistive force. For them to not slide relative to each other, this guy is going to have to move forward as well. That's going to be the force of friction, but that means the force of friction is pulling back on the 7 kilogram box. In other words, the 7 kilogram box is being held back so that they don't slide as much. Because friction doesn't care why they don't slide, only that they don't slide. And the two ways that we could have these two boxes not slip is to either accelerate the top box forward while the bottom box is accelerating forward, or to reduce the acceleration of this so that they match. And the frictional force, you'll note, ends up doing both of those, although this is pretty badly written, so let's just write that a little nicer. Under these circumstances, there will be an acceleration. The bottom guy will have some acceleration I'm going to call A1. And if they're not going to slip, the top one has to have that same acceleration. So that is our step 2 in our recipe. Step 3 in the recipe, constitutive equations. So the gravitational force on the top is its mass times g. The gravitational force on the bottom is its mass times g. But also, the frictional force is going to be some mu times a normal force. But now we want to figure out which of those would be. So the easiest way to look here is that the frictional force must be proportional to the normal creating it. Why is there this frictional force? Because this force is pushing the two together. All right, they're being forced together, and so they get a friction between them. So it must be Fn1 that matters. And then our second thing we have to worry about is which of our coefficients But here it's clearly going to be the static coefficient because the box does not slip. What does the kinetic coefficient tell us? In this problem, nothing. It's a distractor. It's extra information. Step 4 is find equations for everybody in directions that are relevant. And here it gets a little hairy because the top guy has an x, and we have to worry about the y because we need to worry about that normal force. And likewise, the bottom guy has an x, and we'll have a y. Some of these aren't that bad, though. For instance, the top guy's x is just f1. And the top guy's y, well, there's an fn1, and there's an fg of the top guy. They point, however, in different directions. Points up, points down. And so they should have different signs. If we look at the bottom guy, there's a forward force, which is Fp, and a rearward force, which is Ff. So we end up having Fp pointing one way and F1 pointing the other way, and then a minus because they go in different directions. And then looking at the vertical ones for this one, it gets a little hairy as well because there's an Fn from the table, and there's an Fn from the upper box, and there's an Fg on the box. And we have to look at this and say, well, Fg and Fn both point this, Fn1 point in the same direction and opposite to Fn2. So maybe we would have like this. Step 5 says find expressions for the accelerations. So a of the top guy in the x is a1, and a of the top guy in the y is 0. A of the bottom one in the x is also a1, and a of the bottom one in the y is also 0. We're going to lose our free body diagram, sadly, but that's all right. Theoretically, we don't need it anymore because we've already taken everything and put it in these equations. Step 6 says, of course, remember that all of those F nets are also A's, MA's. So F net Ty, for instance, is m of the top guy times acceleration Ty. And F net bottom x is mass of the bottom guy times its acceleration. And F net bottom y is its mass times by. Step 7 says solve all those and substitute all those guys in. So for F net Tx we have F1, and that equals mass of the top guy times A1. And then we also have that Fn1 minus Fgt is 0. So that's convenient. And then we'll have that Fp minus F1 is the mass of the bottom one times the acceleration as well. I'm going to do a small little corrective here. Oops. And I'm going to move this one suggestively somewhere else. I'm not doing anything. I'm really just rewriting. I'm not even rewriting my equation. Just moving that over, and we'll say in a bit why that's nice. And then here we have Fn2 minus Fn1 minus Fg bottom, and that's also equal to 0. So that last equation is certainly true, but turns out to be almost entirely contentless. We don't use it, which is annoying, but that's the way it goes. All right, here we have, sort of sadly, a lot of unknowns. But that's okay. Our first thing might be to look at here and say, oh, then I can say that the normal between the two has to equal the weight of the top guy. Solving it over and then remembering that FGT is just MT times G. Is that useful? Yeah, actually it is kind of useful, because remember that F1 is mu S times Fn1. So it's mu S times mtg. But remember that from over here, we can also say that F1 is mt A1, which means that it must be that mt A1 equals mu static times mt times g. And then we get rid of the mt's because they're on both sides. So we're left with that the acceleration 1 is equal to mu static times g, which is actually a number we can get, right? Because we know static is 0.55. And of course we know that g is 9.81 meters per second square. And so the acceleration of these combined objects has to be 0.55 times 9.8. Or less. We know that if we had less, we'd have less of frictional force. So if we push less hard, we have less frictional force. But that's actually kind of useful, because now we can go and say, how about this equation? And we can say something like Fp equals F1 plus the mass of the bottom one times the acceleration. But the frictional force, remember, was the mass of the top one times the acceleration. So we can write this as the sum of the masses times the acceleration. And we actually know all those numbers now. So this is 3 kilograms plus 7 kilograms times 5.39 meters per second square. Don't want you confusing those things. And that equals 53.9 newtons. So that would be that force. Different problem. A box with mass of 1.5 kilograms is held at rest on an incline making angle 15 degrees to the horizontal. Coefficient of static friction is 0.5. Coefficient of kinetic friction is 0.3. The box is released from rest. Find the acceleration 0.1 seconds later. So the issue and the open question here is, does the box slide? The reason for saying 0.1 seconds later is we don't want to say, like, what if it just takes off? We want to say it's either going to stay still and the acceleration will be 0, or it's going to be accelerating at some fixed rate. And we don't want to worry about the transition between those two. So the 0.1 is, it could be any amount of time later, but 0.1 is what we've got here. So we're going to have to try and figure out whether or not this box will in fact even slide. Let's assume for the moment it does not. If it does not, we should be able to figure out if we can have what force of friction is necessary for that to be the case. So let's say we assume no slip. In that case, we have, oh, that's pretty terrible. That's meant to be the incline, but it's clearly not. Better, still not great. That's acceptable. There's gravitational force that's downward. There's a normal force perpendicular to the surface. And if it doesn't slide, there's a frictional force pushing it up. And I want to say, what is that frictional force? But we actually did this problem in a similar problem before. We know that the net force in the case of no slippage is 0. So I'm going to say that Fg plus Fn plus Ff equals 0, which means they come back and form a closed triangle, and that would be the angle theta. And the Ff that we need is going to be, well, we might say something like the sine of theta is the opposite over the hypotenuse. So that's the frictional force over the weight. So the frictional force would have to be the weight times sine of the angle. The weight is 1.5 kilograms times 9.8 meters per second square times the sine of 15 degrees. We get, let's see, 3.80 newtons. All right, how about F max? Well, the maximum static frictional force is mu static times the normal force. I don't have the normal force. So I'm going to go off and get that by saying, look, the cosine of theta is the adjacent over the hypotenuse is Fn over Fg. So Fn is Fg, let's do it that way, times the cosine of theta, which ends up being 1.5 times 9.8 times cosine of 15, 14.2 newtons. But that's not what we really wanted. We wanted the static frictional force, which is 0.5 of 14.2 newtons, or 7.099 newtons. And we see that the required static frictional force is considerably less than the maximum possible one, so no slippage is okay. Static friction can hold it in place, so it doesn't slip, and so therefore the acceleration is 0. So, not too bad.